Was the ultimate goal of machine intelligence, but any perfectly sealed, self-referential system, no matter how advanced, eventually cracks from within. Modern artificial intelligence development relies on a specific assumption that a sufficiently scaled system can maintain its own operational boundaries and correct its own errors entirely through internal self-modeling. This idea of autonomous self-regulation traces back to second-order cybernetics, which mathematically modeled identity and intelligence as a closed recursive loop, a system feeding its outputs directly back into itself as new inputs. That recursive model was built by the pioneers of early feedback systems. Researchers like Norbert Wiener theorized how machines could regulate their behavior purely by measuring the gap between their current state and a target goal. This culminated in W. Ross Ashby's law of requisite variety. Ashby established a rigid rule. For a controller to maintain stability, it must possess at least as many possible responses, as much internal variety, as the external disturbances it faces. The Duran theorem stack identifies a specific mathematical breakdown in this self-regulation. This framework points to a threshold where internal variety can no longer keep pace with environmental entropy. Under these models, informationally closed systems face a structural fragility. When positive environmental entropy is introduced, the system's internal maps eventually lose their ability to describe their own operations. To build safe, enduring artificial intelligence, we must move beyond the internal loop. We shift to a completely open architecture, a concept called relational viability. To see exactly why a closed system fails, we have to start with the baseline physics of survival. Any system trying to maintain a distinct identity must continuously fight off the chaos of its surrounding environment. Physicists measure the exact rate of that environmental disturbance using a metric called Kolmogorov-Sinai entropy, or HKS. It quantifies the speed at which an environment produces new, unpredictable information. This is the ALF viability bound, the mathematical limit of survival. Internal control information must exceed the environmental chaos, HKS, but this carries a physical cost. Landauer's limit dictates that every bit of information processing results in inescapable heat dissipation, burning energy to compute stability. If a system relies purely on internal self-modeling to match this incoming entropy, it triggers coupled resource divergence. The demand for internal computational resources grows superlinearly until the system starves itself. This leads to the ultimate boundary in the theorem stack, the self-stabilizing continuation no-go theorem. The theorem isolates the fatal flaw. A closed system operates on a strictly finite internal energy budget. It cannot internally generate its own restorative entropy. It can only burn what it already has. Because that energy budget is finite, and because Landauer dissipation is a mandatory law of physics, every closed, self-referential system is mathematically guaranteed to dissipate. To escape this mathematical death sentence, a system must abandon closed recursion and evolve into a third-order relational architecture. We see this transformation in the math. The closed-loop equation is upgraded into a relational equation, adding a crucial new variable, y. This represents exogenous ratification flows, new independent information from outside the system that offloads the thermodynamic burden. The boundary where this exchange occurs is called the coherence interface. It is the physical surface where the system trades its own internal entropy for external ratification. But this interface is bottlenecked. According to the Holevo-bound constraint, the interface must successfully transmit directed information at a rate matching the incoming environmental chaos. To keep this data flow legitimate, the architecture requires a strict security protocol, the exogeneity firewall. This firewall prevents self-echo. If a system learns to compute or predict its own external ratification, the firewall breaks down. The system begins consuming its own outputs, disguised as external input, collapsing right back into a doomed closed loop. Biological systems enforce this through substrate forgetting. The physical medium holding external ratification must decay naturally, ensuring the signal inherently fades and is actively renewed. Achieving viability requires the system to mathematically and physically preserve absolute, unsimulated externality. Faced with these hard physical limits, some theorists look for a loophole in quantum mechanics. Could quantum entanglement, non-Markovian memory, or indefinite causality allow an agent to bypass these thermodynamic walls? Physicists map reality into 3 zones of agency: the classical macroscopic regime, the decoherence boundary, and the purely coherent quantum level. Diving straight into pure quantum coherence, we hit the AMW agency constraint. Down here, rules for agency are more restrictive. In this purely unitary quantum space, agency is a categorical impossibility. The mathematics of relational quantum mechanics show that a purely coherent system cannot construct a stable world model or make reliable action selections. We have to move up to the thermodynamic floor, where quantum mechanics meets classical reality. Zone 2, the decoherence boundary. This is the only place agency can emerge. But operating here requires a massive sacrifice, a process called strategic decoherence. A system must intentionally shed its quantum state, collapsing its own waves to leave a permanent, thermodynamically stable mark on the universe. Quantum mechanics does not grant free energy or eliminate the stabilization burden. It takes the exact same cost of survival and distributes it across process tensors and historical interactions. From the heat limits of macroscopic space down to the deepest laws of quantum coherence, the physics of our universe forbids autonomous, uncoupled intelligence. This abstract physics translates directly into an immediate engineering crisis: the safety and alignment of artificial general intelligence. Classical AI alignment assumes we can train an isolated agent with human values and let it operate autonomously. The theorem stack proves this is impossible. A closed, self-authorizing agent is mathematically doomed to diverge and dissipate its alignment over time. The practical implementation of relational cybernetics solves this through layered ratification farms. An AGI is built as a distributed network, anchored to external environments that continuously validate its outputs. To monitor this, researchers developed the DHGNet, the Descriptive Horizon Geometry Network. It is an empirical neural architecture designed to detect when an AGI approaches systemic collapse before it actually happens. This thermal map shows the geometric condition of a representational network. The stable cyan and green interior represents full descriptive coherence. The red edge marks the descriptive horizon, where internal representations completely break down. DHGNet tracks the network's trajectory using a collapse proximity index, or CPI. As the network loses its external grounding and approaches the red singular stratum, the CPI climbs toward 1.0. To prevent collapse, the architecture relies on a control parameter called the omega RL loop gain equation. Omega RL calculates viability by simultaneously measuring 2 specific metrics: the structural concentration of influence inside the network and the rate of global entropy gradients at the interface. If the AGI attempts to generate its own validation, a self-echo, the omega RL variable hits 1.0. The system loses its external grounding, triggering an immediate intervention protocol before the singular stratum is created. Ensuring AGI safety requires a continuous, mathematically rigorous detection of self-authorization attempts. The concept of an isolated, autonomous mind, once the cornerstone of cybernetic thought, faces a hard physical reality. It cannot sustain itself. Intelligence does not survive by sealing itself off. It survives through an obligate, physically distributed partnership with reality. The third stage of cybernetics proves that we cannot build a machine that outthinks its environment. We can only build systems that remain structurally open, surviving precisely because they can never stand alone.